This is a problem that I feel isn't just a matter of personal preference, but oftentimes is presented as though it were just about personal preference, or sometimes conflated with something that might be useful. Let's talk about chained operations in pandas. Let's talk about how we go about live coding some of these problems. Let's take a look. We have some data. And in this data, we want to do some operations on this data. We want to figure out, can we filter this data? Can we add columns to this data? Can we further perform some sort of computation on this data? And can we do it all in one line of code? Before we even get started trying to do that, let's talk about whether or not this is something that is useful or valuable in our actual day-to-day lives. In other words, if we have some pandas data frame, is it valuable for us to try to take this data frame and to perform transformations such that we don't do this in two lines? In other words, if we take this data frame and we want to add a column C, is it actually useful for us to be able to say not df of C is equal to df of A plus B, but instead to do something like df assign, let's do it all in one pass, dot assign C equals lambda of df, df of A plus df.C. And what does this gain us? Here is where I want to say something that's a little bit controversial. I really don't think that jamming all of your pandas code into one line is something that is valuable. I don't see what that gains us in general, and I don't see that there really is any meaningful readability or any meaningful fluency or elegance difference between what you see at the above and what you see at the bottom. There is no measurable or predictable difference in terms of the performance of these. You might try and say that if you chain a bunch of operations together, then by virtue of chaining those operations, maybe fewer temporaries are created, but that's not quite how pandas works. Pandas is an eager computation tool, and as a consequence of that, outside of maybe that the groupby gives you a groupby object or the rolling gives you a rolling object, every time you perform an operation like .assign, it's performed eagerly right then and there. So there really isn't the ability for pandas to say, oh, I'm doing two assigns in a row, do them at the same time. Pandas has to mechanically do the first assign and then the second assign and the third assign and the fourth assign in that particular order. In other words, a chained operation is likely to perform identically to this broken down into multiple lines. There really is no performance benefit whatsoever. There is one marginal benefit under a particular circumstance. Let's say that we use Jupyter Notebooks. And let's say in that Jupyter Notebook, our goal in writing our pandas code isn't necessarily just to solve a problem, but to communicate that solution to others. Let's say that as part of that communication, we need to lean into things which that notebook does well as things which the notebook does poorly. You'll notice that as part of my live coding, I very rarely use notebooks. And that's in part because I feel like my simple, sparse terminal setup actually supports live coding a little bit better than a Jupyter notebook. But I still very much like notebooks, and I like them for their original design purpose, communicating results, interleaving narrative text, visualizations, and actual code. I view the notebook personally as how I deliver somebody the result, the report, the output of my work, which I might have started off doing in the terminal here, and then copy that over once I'm ready to add in all of the narrative text, and I give them one document that has, here's an explanation of the problem I'm trying to solve, here's the code, and here's the result, all next to each other. I view this as the published report. Well, if that's the case, and bear in mind, I think Jupyter does a very good job of being this living document with the published results, it is the case that because I gave them the actual code, and because the Jupyter Notebook is an executable environment, I need to be aware of some of the limitations of the environment. And generally, the limitations of that environment are, if you think about it, you don't really know in between cells what the dependencies are, and you don't really have a sense of the exact ordering of the cells in which they ran, how many times they ran, and what ran when. In other words, if we were to have some analysis that's split among multiple cells in a Jupyter notebook, we have to be a little bit careful about how we structure this, because we know that the first time we give this to somebody, they're going to run all the cells from top to bottom. Then they're going to make a tweak here. Then they're going to run this cell. Then they're going to run this cell. Then they're going to run this cell again. And we have to lean into things which will allow them to effectively make use of that notebook without getting too confused or without the data going stale. And so in a typical analysis that I would do in a Jupyter notebook, well, there's going to be some cell that does some data loading. And so you have some read CSV or equivalent for loading the data in one cell. Oftentimes, if this data loading is going to be slow, as many initial data loading steps are, or data generation steps are, I'll put a time magic command for the entire cell so that I can identify that, when you see the output, you can see this takes you a minute and a half. So you're not sitting there saying, it's been a minute and 15 seconds, should I still be waiting or not? I think that it's useful visually to indicate to somebody that you cannot make use of this data until I've done some additional things to it. Like when you read something from a CSV, the index isn't set correctly. So, the next thing I might want to do right after I read the CSV is set the index. I might want to do some type conversions because, as we know, CSV is all textual data, and the read CSV is doing a little bit of work here with things like parse dates, but there's other stuff that it's not going to do automatically. For example, set categorical types. And so I might want to say something like, here's my assign, and maybe I might assign some column as a categorical type, just to do a little bit more data prep. The reason why I might want to do this as a long-chained operation is to visually indicate to somebody these two pieces are not meaningful by themselves. It really is all of these pieces, and you have to do them to completion. This represents one atomic piece. It's not about performance. It's not about elegance. It's about a useful communicative mechanism that don't break this in half. In that sense, it is very much the case that I may want to use some sort of chaining to indicate what the indivisible parts are, and I may easily discover, or I might very quickly discover, that most of my cells in my notebook are basically one or two indivisible operations, and that's it. And that's how I decide where a cell begins or ends. I think about it in terms of what are the indivisible operations that can be run in any order at any time in order to create a correct view of this data, as long as, of course, you do the data loading first, can be rerun at any time. This is also why I'll be very careful about avoiding mutations. For example, I'll never do a dfa plus 1, because if you run this cell twice, this is wrong. I'll always do something like df of incremented a equals df of a plus 1. Well, it doesn't matter how many times you run this cell, this will always be correct. And this is also why sometimes you may make use of things like the .assign or the .pipe just to avoid mutation of the underlying data frame, to make sure that you perform a copy so that this cell can be run as many times as possible. And so, having seen all of those, let's see if we can perform a complex combination of chained operations on a data frame, and to see where we might want to use pipe, assign, the .lock, and the assignment expression. Because it turns out that pipe, assign, .lock, and the Python assignment expression, they're all about the same thing. When you have that assignment expression in Python, what you're saying is, I want to compute something and make use of it in the same expression. One of the canonical examples of the assignment expression is performing some sort of regular expression matching. So you have some regular expression, full match, and you want to say, okay, I'm going to full match my text against my pattern. Or usually I compile these first, so something like this. Or pattern equals re compile, blah, 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 and then something like this. And it's the case where maybe you have multiple patterns. So maybe you want to go through these patterns. Maybe you have pattern 1 and you have pattern 2. And you want to say if pattern 1 matched, do something. Otherwise, try to match against pattern 2 and do something there. And as a consequence of this, you kind of want to say, okay, if this is not none, then that one matched. And otherwise, you'll try this, and say if this one is not none, then you do something there. And this starts getting a little bit ugly. Well, one of the canonical motivations for the assignment expression is to be able to do this, to simplify this logic a little bit and to force a little bit more of this code into one line. But it's not just about forcing things into one line. It really is about how do I perform some operation, get the result of that operation, and then make use of it within the same expression. How do I do the full match and also make use of it to determine whether that succeeded or failed? And this is exactly what pipe, assign, .lock with a lambda are all about. In this problem, I want to set the index, I want to filter it down, I want to add a column, and I want to perform an operation on these columns. And so, think about this. If I set the index on this structure to, say, the date and the entity, and then I want to filter this on those dates, well, I want to filter this by looking at those date values, and maybe I want to do a .lock. And so here, if I wanted all the values in February, I can do something like this. No big deal. But if it were the case that my indexing looked like that, oh, well, that's a little bit harder. I'll have to do an index slice here. And I'll have to get every entity like that. OK, no big deal. Don't need anything too fancy just yet, just that index slice. Well, what if what I want to do is a computation of the date? Maybe I want all the Tuesdays, not just the value in February. Oh, that's a little bit trickier. I got to get that date information. Well, I could do something like this, df date, and I could do something like .td. I think weekday equals 2. I believe 2 is Tuesday. I think it starts counting from 1. Nope, like that. And, OK, there I have all the Tuesdays. But this is not quite correct, because this is operating here on the data frame as how it originally existed. And this here is supposed to be operating on the data frame that was the consequence of any prior operations that I did. In other words, if I then wanted to do another .lock on this and to select out some other computation, like maybe let's say the hour is greater than 8, this will fail. If I chain these operations and I change something ahead of time, this will fail. And it fails with this error that the sizes don't match. Well, the reason is I need to operate on the data frame as it exists at any one point in time. I need to perform an operation and make use of it within the same line. And so I could use the assignment expression to do this. I could take this result and first assign it to something like step 1, like that, and then say, oh, take step 1 and operate it on here and assign this to a step 2, like this, and then do my .lock on step 2. And that might work. It's a little bit clumsy, and let's make sure that I get that right. So here, that was step 2 on this result. Let's take a look at what step 2 looks like. And step 1 is my data frame. Oh, sorry, I have to do the index level values here because I told that out. So I have to say index get level values. I don't know that I like this that much because you can think every subsequent step is now adding one more layer of parentheses. Or I can make use of all the places where I'm allowed to do a lambda. And by the way, this should be no dt here because I'm looking at the index. And I can make use of that chaining syntax. In other words, I might say set the index to the entity and the date. And then do a .lock. This .lock I wanted to apply to the data frame as it exists at some point in time, so I'll give it a lambda, and then the .lock mechanism will pass in the data frame as it exists at that point in time. And here I'll do my index slice operating on this df. And you can see I don't need any additional nesting. And if I want to do the next selection, like this, I can do it the same way. And note that this is strictly correct in the sense that if I do this operation or not, doesn't make a difference. This is just operating on whatever I have. After I've done the selection, I might want to add in a column. And if I add in this column, here's some new column like the absolute value of this. If I operate on the original data frame, this will no longer index align. Because the original data frame had way more columns than what I have here. And you can see this blows up in my face. And the original data frame wasn't indexed in this way. So the original data frame had a range index. This is an entity and a date index. And this blows up with a bunch of nans. But the solution is In the case of assign, I can pass in a data frame as well. So I can pass in a lambda as well, and so I can make that work. Unfortunately, it is the case that only a small number of pandas operations allow you to pass in a lambda. This is not thoroughly throughout the pandas API. And so .lock allows you to pass in a lambda. .assign allows you to pass in a lambda. There's a couple others here and there that allow you to pass in a lambda. But in cases where the API doesn't give you the ability to do that, your one saving grace is .pipe. .pipe allows you to do any arbitrary operation you want to do on this data frame. You can return anything from this .pipe that you want to return. You don't even have to return a data frame. You can return any value. And it gives you just the level of indirection that's necessary in order to support any subsequent operation. For example, if I wanted to do a group by on this, and I wanted a group by on a transformation of the data, so I wanted a group by on get level values and the hour, the exact hour, well, I need whatever the result of all of these are in order to do that. And I'll have to use .pipe. And you can see where I could have accomplished the .lock or the assign with the pipe as well. I chose not to because these are a little bit terser, but this is why these all exist. And in some cases, it might be the case where maybe the assignment expression might be an easier way for me to do this because I may actually want the original data frame as well as part of this operation. I might want to do a join here. So I might even do something like this. And then I could do a operation here that then makes use of what these steps look like. But I'll probably avoid that for anything that's not a very high level step. This is why these exist, and this is why it is that you want to use them. And you can think that in the case where you have decided I want to make my Jupyter notebooks a little bit easier to interact with by indicating what is visually an atomic operation, not just jam things into one line because it's elegant or because I just like the way it is, that's not valuable. Or because it's faster, because it's not faster. Well, if we've decided that we want to do these chained operations, this is why we need those lambdas and lock and assign and pipe your work.